Okay, right on time. It's 4 o'clock, so we're gonna get started again. I hope everyone had a chance to stretch their legs, refocus their eyes. All right, our next talk is by James Dabney, entitled Using Assume Guarantee Contracts in Autonomous Spacecraft. All right, James.
Okay, well, thank you. So I'm Jim Dabney, and my co-authors are Pavan Rajagopal of CACI and Julia Badger of NASA JSC. So we can go to the next slide. So I'm going to talk a little bit about the motivation of why we're doing the assumed guarantee contracts, and then I'll explain what we mean by assumed guarantee contracts, and then talk about how we're using them in development early in the life cycle, and also in operations at runtime. And then we'll talk about future work. So if we go to the next slide. So the spacecraft, as we all know, are becoming more complex and more autonomous. We're working on the Gateway Vehicle Systems Manager. So the Gateway is a part of the Artemis project to return to the moon, and it's a space station that orbits the moon, or will orbit the moon. And it needs to be able, the vehicle system manager needs to be able to manage the spacecraft systems for extended periods of unattended operations, as well as to work when the system is being controlled by the ground or when it's crewed. So the vehicle system manager coordinates among numerous subsystems and modules that are provided by team members from around the world. So we can go on to the next. This slide shows the standard verification V that you'll find in any systems engineering text. And so the basic idea of the verification V is that on the left side are the steps in a classical project flow from requirements analysis to implementation. And then the verification works up the right side of the diagram. We start doing the verification activities, the testing, when there's something to test. And then as the pieces are integrated, the testing proceeds to the final testing of the validation testing of the integrated system. So that's a process that's been used for a long time, and it works, but it has some problems that we have discussed earlier today. And the biggest one from our perspective as being involved in verification of the Gateway VSM software is that about 70% of the problems, and those are typically the hardest to fix problems, are introduced very early in the life cycle in the specification phase, but they're not found until we get into the verification phase on the right side of the diagram. And as a result, they can be very expensive to fix, and also time consuming to fix. And because of the fact that like all projects, we're on a compressed budget and also a compressed schedule, we can't tolerate that any more than we absolutely have to. So the next slide shows the cost aspect of this problem, and this is from a number of sources that we located several years ago for how the cost evolves for when you find a problem for the different kinds of problems. So the top row is the one that's the most problematic, and that is if it costs $1 to fix a requirements problem that you find in the requirements phase, it's going to cost about $130 to fix that same problem if we find it in the integration phase, which is where we're most likely to find it using the standard verification V approach. And of course, finding it late also requires a lot more time to fix it, which is also a problem. So that's the motivation for finding ways, and some that we've discussed today with model-based system engineering and the digital design, to find those problems and get them fixed early in the life cycle. So we go on to the next slide. So the approach that we are using to augment the verification process, and it's certainly not replacing the activities in the verification V, but it's augmenting them for both early life cycle and in operations, are using assumed guarantee contracts. So assumed guarantee contracts are a means of specifying the expected behavior of systems and subsystems and components in a hierarchical way. And it consists of the assumptions or preconditions that bound the condition in which the contract applies, and the guarantees specify the post conditions or the outputs, things that the system must supply when the contract is valid, that is when the assumptions apply. So we can use the assumed guarantee contracts to define safety properties or hazard controls. In an example that's a non-spacecraft would be that you may have the requirement that the car won't start unless the transmission is in park. We can convert the assumed guarantee contract stated in just into text form into a mathematical specification that can be checked using model checking tools. And so that's the basic idea of the process. And that ensures that the system has the desired behavior and the safety properties that we are specifying. So we go to the next slide. Well, this shows the flow down of the contracts from in our case, from the vehicle system manager to both internal components or internal subsystems in the vehicle system manager itself, as well as the external subsystems that are in different modules provided by different people. We can use the assumed guarantee contracts in a hierarchical way, and at each level they're checked using a model checker using the standard model checking techniques. So the flow down can simplify verification by focusing on one component at a time, and that's always important when we're doing model checking, because we have a state space explosion problem that if we don't modularize things, we don't break it down, will result in the system failing. So the model checker determines if a finite state machine that implements the contract satisfies the given specification. Okay, so go to the next slide. This is the template that we're using to specify the assumed guarantee contract. So the contract, a single contract has the 5 parts. The variables are the inputs, and these are the values that are supplied to the function or the module or whatever the contract is, and the outputs are the values that are returned, what the guarantee gives us. And then each of those, the inputs and the outputs, have data types. And the data types can be custom, and often they're going to be custom things. That is, that they don't just have to be an atomic thing, such as a Boolean or an int. They can be a complex data structure, commands, that sort of thing. So there's not any real restriction on what either the inputs and outputs are. They're just anything that we can reason on. We can work with. The assumptions are the conditions and the constraints on the inputs under which the contract is valid. And so the contract itself always has those 2 parts. It has the assumptions that tell us when the contract is valid, and then the guarantees, which are the things that the system is guaranteed to do, the outputs that it's guaranteed to produce when the assumptions hold. Okay, go on to the next. So we generate the contract starting with textual requirements, such as from a system specification. And examples that are given here, one is when an executive receives a command, and we'll look at this one in more detail, that it will respond with an accept reject. So those are the 2 possible responses within 5 seconds or some time limit. Or we can have a contract that the executive will provide task updates at a specified rate, or a contract that after accepting a command, so this is going to be a subsequent contract to the first one, they will respond with a completion message within a certain number of seconds. Where we get these things are typically from parts of a specification that can be represented conveniently using a state machine. One of the most common kinds of requirements errors that we have seen in the past are complex requirements that involve tables. I've seen requirements that a single requirement is, it says that the system will satisfy this table, and the table has maybe 50 rows and several columns that represent the different aspects of it, and it's not even uniform in what the commands will do and what the responses are. And so those are the kinds of things that are nearly impossible to verify analytically, and which are very well suited for modeling using state machines and then checking using the assumed guarantee contracts. Okay, the next slide. This is an example of a contract using the template for the command with task statement. So the inputs is a command with tasks, and so that's going to be as a data type that's a command that has tasks, and that will be with an enumerated set of things, and then the output is just accept or reject. And the system might reject the command for any number of reasons. Maybe it's busy and can't do that. Then the types for the command is a command message for the input, and for the output it's a response message, which in this case is pretty simple. The assumption, the executive receives the command from a valid set, and so that's what I said, that the inputs have to be from an enumerated set, and then the guarantee is that it sends the response from a valid response set. So those are very straightforward things to implement in a logic programming language, and it takes a ambiguous table specification and makes it into a rigorous checkable specification. Okay, so then go on to the next slide. So we've talked about what the contracts are. We're using the contracts in two different parts of our verification operation. The first is during verification, during development, which is early life cycle activities. And this is, as I said, for contracts that can be represented as state machine kinds of functions, such as the table that I discussed. We can specify the state machine and the contracts in a modeling language such as Promula or TLA plus, and then check them using a model checker such as SPIN or TLC. And then a contract violation may indicate a specification issue, either in the specification itself or of course it could be in our model, but it's something that would then need to be fixed either way. So those are the development time assumed guarantee contracts, and we'll talk about those more next. And then we also have operational contracts, which protect us from divergence, kind of watchdog sorts of things, the divergence, deadlocks, and live locks in operation. And those are going to be fewer in number than the development contracts because of the problem of operational overhead. And those we can implement using a lightweight checker such as R2U2, and then the failure of a contract or a verdict of fail would trigger some corrective response. Okay, move on to the next slide. So this is the workflow for the development contract. So we first developed a set of contracts from the specification that's driving the process. And then for each in-scope contract, we identify the inputs and to populate the template, identify the outputs and the data types, and then identify assumptions and guarantees. And this is for a single contract. We identify all the assumptions for when it applies. Sometimes it's very simple, sometimes it's a very complex logic statement. the same for the guarantees, and then implement that in a formal specification language, such as TLA Plus or Promula or in any of the other languages of that type. And then we can verify that specification using model checking. And the verified models can be used to drive code generation, and also to drive a test case generation for using when we get to the verification phase of the life cycle. Go on to the next slide. So this is using the formal specification to develop the test cases. So we start with the TLA specification and some metric for the coverage of the goals, generate test cases, and then those test cases work with the code and to give us verified code. So one of the things that we can do was, once we've verified the specification using the assumed guarantee contract, that in a sense gives us a regression test that we can use with the implemented code. Okay, next slide. There's a number of languages that we considered, and most of them are research quality. They're university research groups that are producing good results, but it's not things that are suitable for operational use just yet. The best option that we could find was TLA Plus, which has a front end called PlusCal, which makes it a little easier to generate the specifications. TLA Plus has been around for a fair amount of time. It's easy to learn. There's some good, it's developed by Leslie Lamport and has some really good online training and also a good textbook. And so most organizations are reporting that they're getting production quality work within 2 or 3 weeks. And that's consistent with our results from doing some pilot project. It's easy to read, and it's open source with a large support community, and it's been used in the real world in some really big projects, such as at Microsoft and Google. Okay, the next slide. Operational model checking or runtime model checking is a form of runtime verification. And there's a number of approaches that have been proposed for doing it. The first and the most simple is to check current state traces. So this would be like telemetry feeds or something from the monitoring a data bus, to check the flow of states using temporal logic, either looking back, or it can also be done looking forward. And then some more complex approaches would be to look forward using a linear state propagator a few steps, or to do even complete model checking online, where we're using the current state as initial conditions for a model checker. So the first two approaches are both feasible, and they're good tools for doing it. And there's also been some good results on the linear state propagation for a few steps. The streamlined model checking is not computationally feasible right now. So then we found that with careful tailoring of the contracts and using good tools, that the computational cost of runtime verification can be minimized, and it can be a very good technique. So go on to the next. The candidate tools that we looked at, there are few that are at a suitable TRL for this work. We looked at Copilot from Langley, which is being used in small UAVs. It's a pretty tightly coupled approach, but it is a fairly mature tool. We looked at Lola from the University of Saarland in Germany and in the European Space Agency. It's a tool that reasons on data streams and looking backwards, and it's currently being extensively revised. So it turned out that even though it's a nice tool, it didn't seem to be a good fit for us. And then R2U2, which comes from Ames and the Iowa State. And if you can learn more about that, tomorrow afternoon there's a presentation from Kristen Rosier of Iowa State on R2U2 and their progress and plans for it. It also reasons on data streams and can look look ahead with some linear state propagation, and it's a very lightweight tool, and it's based on the experiments that we did. R2U2 is the tool that we're going forward with. Okay, and go to the next slide. So we assume guarantee contracts are the formal specifications or are a precise mechanism for behavioral specification and verification. And importantly, we can use them early in the life cycle for doing development verification to make sure that our specification is correct. And we can also use them in runtime to make sure that the system behaves itself. We can model check the formal specifications using TLA+, and we've prototyped that with a couple examples and found it to be quite doable and easy to learn. And also we've prototyped some runtime, both using offline and online application of R2U2, and found it to be feasible, easy to learn, and a very promising approach. So you can go on to my last slide. The future work, what we're working on next for the development contracts, are to expand the scope and then develop templates and training. And for operational contracts, there's a number of adjustments to R2U2 that we're looking at to make it easier to program and to make it feasible for us to develop a template to flow contracts from the development contracts to the operational contracts. So I'm done with a little time. If there's some questions, that would be good.
Yeah, looks like we do have one in the Q&A from Peter Fiddleman. Could assume guarantee contracts include assumptions, guarantees of function execution time, or are functions just modeled as pure mathematical functions that transform inputs into outputs with no side effects or time taken?
So the answer is that time can be taken into account, and that's kind of built in. That's to R2U2 as a metric temporal logic. A little bit different depending on whether you're talking about the development time or the runtime, because just of the different tools. But in general, yes, that is possible, and that's kind of important to do.
Okay. Next question from Leonidas Cosmides. Why have you not considered Ada Spark? Let's see. Sorry if you didn't mention it and I missed it. I wish, or which was as far as I understand, also supports assumed guarantee contracts and runtime verification.
We looked at lots of different tools, and the ones that we found the most promising are the ones that I mentioned. But there are lots of tools, and generally speaking, what we found was that they're tools that are good quality, but they're also fairly early in the life cycle and not deployable. There are also some commercial tools to consider. This is a big space of things that you can use for doing, particularly the development time, assumed guarantee contracts.
Okay. Probably have time for one more question, but let's see if anybody has one. We've otherwise exhausted our list.
Chris, we have one in the chat from
Joel. Oh, we have one in the chat. Okay. Let's see. Okay, would using ears improve the requirements and by implication the contracts?
So I don't know what ears means, so right.
I don't. Yeah.
The question.
EARS. Okay. All right. Maybe. Okay. Thanks a lot, Jim. Great presentation.